Hi, everybody, and welcome back to Unit 6, Lesson 6, which is an introduction to indefinite integrals. Today we have two learning targets. The first learning target for today is I can find the antiderivative of a function f. So we've learned about derivatives, and now we're going to be learning about antiderivatives. The second learning target is I can express the indefinite integral of a function as the antiderivative plus c, where c could be any constant. So we're going to learn about indefinite integrals. We're going to use antiderivatives to do that because an indefinite integral can be expressed as an antiderivative plus c. So antiderivatives are the tool that we use to find an indefinite integral. So before we do that, let's start with a little bit of derivatives review. So I want to go back to what we spent a lot of first semester doing, which is finding derivatives. For this first problem, if I were to find the derivative, I would put f prime of x is equal to, and then I would have the derivative of x squared, which is 2x, plus the derivative of 3x, which is 3, and then the derivative of 8 is just 0, so that would be gone. For problem number 2, my derivative would be f prime of x is equal to the derivative of x squared, which is 2x, plus the derivative of 3x, which is 3, and then the derivative of minus 100 is 0, so it's gone. Next, if I have problem number 3, I would find the derivative, which is the derivative of sine, which is cosine of x, and the derivative of 8, which is 0, so it's gone. And last but not least, the derivative of sine, which is cosine of x, and the derivative of 10, which means it's 0, so it's gone. Now, one of the things I want you to notice here is that even though these two problems are not exactly the same, these two functions, the derivatives are the same. Even though these two functions are not exactly the same, their derivatives are the same. And a reason for that is that that last term in all of those equations was a constant. And the derivative of a constant is 0, which means there's no evidence of it in the actual derivative if you're looking at it. You can't tell that there was an 8 here just by looking at the derivative. You can't tell that there was a minus 100 here just by looking at the derivative. Same thing with the 8 and the minus 10. You can't tell that they were there just by looking at these derivatives. So, how does this play into indefinite integrals? An indefinite integral is an integral whose bounds are not defined. So you'll see the integral symbol here, but there is no lower bound and there is no upper bound. So that is what makes it indefinite, is that the bounds are not defined. Now, even though it's not a definite integral where we have bounds, we're not going to be finding areas here, we can still evaluate or express the answer of an indefinite integral. And in order to do that, we use an antiderivative. We use the term antiderivative to describe the process of undoing a derivative. So this is a process. An antiderivative is a way of thinking backwards. So if you know the derivative, can you find the original function? For example, if f of x is equal to x cubed plus 8, then the derivative would just be 3x squared. Now, if you know that f prime, the derivative, is 3x squared, then you should be able to think backwards and say, okay, well, if the derivative is 3x squared, then I know that the original function would have had to be x cubed because the derivative of x cubed is 3x squared. And then here is where that constant matters. We're going to put a plus c. Now this plus c, what does that mean? Well, if you look at the review examples, you'll notice that the constant term always disappears in the derivative. That's because the derivative of a constant is always 0. So you'll notice if you look at these original problems, there is no evidence of the plus 8 or the minus 100 or the plus 8 or the minus 10 in the derivatives. This plus c is a placeholder for the unknown constant value. So since we don't know what number was there, for example, in this one, you see there was a plus 8. We can't tell that there was a plus 8 there just by looking at the derivative, but it might have been. So since we can't determine the value of that constant just by looking at the derivative, we write plus c as a placeholder for the unknown constant value. We don't know what it is, but we need to save a spot for it. I like to think about this as kind of being like calling dibs when you get in a car, like save my seat. You don't know if there was a constant there because when you took the derivative, it became zero. But you need to save a seat for that constant in the equation, so you put a plus c to save that spot. All right, now we need to talk about how to think through finding antiderivatives. So, for example, in this problem where we started by taking the derivative, we got 3x squared. It was pretty obvious that then the antiderivative would be x cubed because we could see that happening. But how can you generally think through these problems so that for any equation I give you, you can always think backwards to find the antiderivative? In order to do this, we need to review, first of all, how power rule works. When you take a derivative using power rule, there are two steps. First, you multiply by the power. So you take whatever exponent was already there and you drop it down. You multiply. So first, you multiply by the power. And then you take that power that was already there and you subtract by 1. Well, if we want to do the antiderivative, we need to reverse not just the operations that we did, but the order in which we did them. So in order to undo the power rule, we're going to start by undoing the fact that we subtracted the power by 1. The first step then is going to be we are going to add 1 to the power. So if you see that the problem has an x squared, then your antiderivative is going to have an x cubed. Then we need to undo the fact that we multiplied by the original power. So in order to undo that, we are going to divide by the new power. So remember how we added 1 first? You need to divide by the power that you got when you added, not by the power that was already there. So this sounds really complicated, but it's going to take a little bit of getting used to. I think you'll find it's okay after if you practice a little bit. It's going to take a little bit of getting used to because we're now thinking backwards from something we did for a long time. So here are some general kind of examples of ways to write this out to show this. So constant functions. Let's say that you want to integrate just a number. It just says like the number 8 there. Well, when we take a derivative, we get a number, like we got the number 3 here, when the original problem was just the number times x. So the antiderivative of a constant is going to be the constant times x. And then you always have to write plus c at the end to save a spot for some unknown number that might have been there. For example, if I say find the integral, now this is indefinite, there are no bounds, the integral of 8 dx. Your answer would just be 8x. And then you would write plus c to save a spot for that constant that might have been there. Now, you can always check your work by doing the derivative. The derivative of 8x would just be 8, so you're good. And the derivative of c would be 0. That's why there's nothing here. So you can always do the derivative to check your work because this is going to take some getting used to as we kind of get started. Now, if you have a polynomial, you need to use undoing power rule steps that we just talked about to undo that. So the first thing that you would do is you would take your power that's already there and you would add 1. So you would do whatever's already there plus 1. Then you're going to divide what you already had by your power. So there was already an a here as some sort of coefficient, maybe a 3 or a 4. You're going to divide by the new power, n plus 1. And then you need to put a plus c. So how does this look when it's in action? So when I want you to think about doing this antiderivative as you're not just going to come up with the answer in one step. You need to kind of go through the process. It's a 2-step process. First, I'm going to add 1 to the power. So I'm going to write down the x, and then I'm going to add 1 to the power. So if this is a 2, my antiderivative would have been a 3. Then I'm going to divide by the new power. So if this is a 4 that's already here, I'm going to divide by that new power, the 3. So you can see it's a two-step process. First, add 1 to the power, then divide by the new power. And then I'm going to put a plus c. Now, you can always check your work here. If you just take the derivative, so you drop the power, if you multiply by 3, these 3's canceled, you get 4x squared, which is what we started with, so you know you're good. Now, the only time when you cannot use power rule is when, and this is really important because this is really challenging every year, is when there's a power of -1. Now, the reason you can't use power rule when there's a power of -1 is that when you try to add 1 to that power, you get 0, and it doesn't make sense that your function would have started with a power of 0. So we cannot use this because it literally doesn't work. You end up with a power of 0 in your answer, and that doesn't make any sense. If you see the integral of 1 over x dx, I want to remind you first of all that this is the same thing as x to the -1 power. If you have a -1 power, then your original function would have been a natural log function. Now, it's been a long time since we talked about derivatives of natural log, but the derivative of a natural log is 1 over the stuff that was inside of the natural log. So your antiderivative here would be the natural log of the stuff. Now you'll notice I'm putting an absolute value there. That is because the natural log has a domain restriction where you're only allowed to use positive numbers. So to make sure you don't get an undefined value, you need to put an absolute value there. And then you would put plus c. Now, for example, if I said find the antiderivative of 3 over x, even if you tried to use power rule starting from here, the first step would be adding 1 to the power. A -1 plus 1 is 0, so it doesn't work. So instead, as soon as you see that there's a denominator with an x whose power is 1, or a -1 power, then you're going to just say this is a natural log function. So your answer would be 3 times the natural log of the absolute value of x plus c. And again, it's absolute value of x because of the domain restriction for logarithms, which says you can only use positive numbers as inputs. So you need to make sure that all your inputs are positive, so we put an absolute value there. Now, this does not apply to powers of other negative numbers. So this is literally only for powers that are -1. If your power is a -2 or a -3 or a -5, this does not happen. And so we're going to look at some examples now where we use power rule for other types of powers. So let's look at problem number 1. For problem number 1, if we want to find this antiderivative, if we want to evaluate this integral, we're going to do this one term at a time. So for the first term, I'm going to start by writing down my x, and then I'm going to take my power and add 1. So instead of a 2, it's going to be a 3. And then I'm going to divide by my new power. 3 divided by 3 is just 1. So I'm done. That's my answer, x cubed. Plus. Now the invisible power here is a 1. So I'm going to start by copying down my x, and I'm going to add 1 to my power, which gives me a 2. Then when I divide by 2, 2 divided by 2 just gives me 1. Last but not least, this is just a 7. So my antiderivative would be a constant times x, so it would just be 7x. And then I need to put plus c. And the reason I need a plus c at the end is to save a spot for that imaginary constant that might or might not have been there, we're not sure. And so my answer, I'm just going to write it a little bit more neatly, would just be x cubed plus x squared plus 7x plus c. And we can always check that by taking the derivative. So if you take the derivative, you would get 3x squared, which matches this, plus 2x, which matches, plus 7, which matches, and then nothing because the derivative of a constant is 0. Now let's try number 2. So number 2 says 5 over x cubed plus 6x to the fourth. The first thing that I like to do for these is I like to rewrite this with negative exponents instead of fractions. So what I really want to find here is the integral of 5x to the negative 3 power. I'm just rewriting that with a negative power plus 6x to the fourth dx. Now I'm going to do this one term at a time. So the first thing I'm going to do is I'm going to add 1 to my power. So I've got x, and when I add 1, negative 3 plus 1 would be negative 2. And then I'm going to divide by negative 2, so I get negative 5 over 2. Then I'm going to do plus, and now for my next term here, if I take my x and I add 1 to the power, I get 5, x to the fifth. And then if I divide by 5, I get 6 over 5, x to the fifth. And then I'm going to put a plus c at the end to save a spot for that constant that might or might not have been there, but we need to save him a spot either way. So for the next problem, you'll notice we have exponents that are fractions. The good news is you do this the same way we did all the other problems. Nothing new here. The first thing I'm going to do is add 1 to this power. So 1/2 plus 1 would just be 3/2. And then I'm going to divide by 3/2, which is the same thing as multiplying by 2/3. Now, when you divide here, you just get 1, so it's just x to the 3/2. For the next term, we have x to the negative 1/2. Now, negative 1/2 plus 1 is positive 1/2. And if you divide by positive 1/2, you just get 1. And so then at the end, we're just going to put plus c, and that's my antiderivative. And last but not least, we have a problem with a root in it. Now, I like to rewrite roots as exponents. So this would be the integral of 4x to the 2/3 plus 3x to the a 1/2 x. A square root is a 1/2 power. There we go. And then I would have dx. Now I'm going to do this antiderivative one term at a time. So first I'm going to take this first exponent, I'm going to add 1. So 2/3 plus 1 is 5/3. And then I need to divide by 5/3. Now 4 divided by 5/3 is hard for me to do, so instead I'm going to multiply by 3/5. You can just multiply by the reciprocal. So I get 12 over 5 plus, for the next part, I'm going to add 1 to this exponent. So 1/2 plus 1 would be 3/2. And again, I need to divide by 3/2, so I'm just going to multiply by 2/3, which means the 3 and the 3 cancel, and I just get 2. And then I'm going to put plus c at the end. And that's my answer. Now, in my opinion, undoing power rule is definitely the most complicated antiderivative. That's my opinion. And the reason is because there are lots of steps here. Really, the key to every other antiderivative is just to know your derivative rules. So what I've done here is I've listed all of the antiderivative and derivative rules that you need to know. So the antiderivative, or the integral of sine, would be negative cosine, because the derivative of cosine would be negative sine. So you have to kind of think backwards. I've listed them all here for you to go through and review. So the integral of secant times tangent would just be secant, because the derivative of secant would be secant times tangent. The antiderivative of secant squared would be tangent, because the derivative of tangent would be secant squared. So again, like, this all comes back to kind of where these derivative rules came from. You'll notice down here I listed the logarithm rule again. If you ever have a power of -1, or a power of 1 that's in the denominator, it's going to be a logarithm rule. And so you're going to do the natural log of the absolute value of x. And then if you have an x and also the natural log of a number down there, then that means it was just a log with a different base. So all of these are rules that you should definitely go back and review, but I'm not going to take too much time to go over them right now because really the best thing you can do for yourself is to review, make yourself flashcards or something, and then practice. Here are some examples of what I mean by really the key here is just to know the rules. If I tell you that you want to find the integral of 3 cosine theta plus 4 theta d theta, then you're just going to do the antiderivative one term at a time. So the antiderivative of cosine would just be sine because the derivative of sine is cosine. So you would get 3 sine of theta. And the antiderivative of sine would be negative cosine because cosine gives you negative sine. So then this should have been a negative. And if it's not, that means your antiderivative is negative. So negative 4 cosine of theta. And then, of course, don't forget your plus c. The antiderivative of e to the something is just e to the something because the derivative of e to the something is just e to the something. So the antiderivative of 3e to the x would just be 3e to the x. And then the antiderivative of 4, just like we did on the other page, would just be 4x. And then you would have the plus c at the end. For number 6, you can see we have a denominator where there's an x with a power of 1. So in other words, it's the logarithm rule. So we would have 5 times the natural log of the absolute value of x. You always need to use absolute value because, again, of that domain restriction with logarithms. And then the antiderivative of secant tangent would just be secant. So it'd be minus secant of x plus c. And then last but not least, for number 8, the antiderivative of 2 to the x, it's a lot like e to the x. So just like the antiderivative of e to the x was just e to the x, the antiderivative of 2 to the x would be 2 to the x. But the rule for taking the derivative of 2 to the x says that you would also have multiplied by the natural log of 2. Since that isn't here, we need to undo that by dividing by the natural log of 2. Again, the rule for the derivative is that the derivative of 2 to the x is 2 to the x times the natural log of 2. I'm going to write this down. I've decided. The derivative of 2 to the x would be 2 to the x times the natural log of 2. And since the natural log of 2 is not here, you would just have to divide by the natural log of 2 because you have to cancel it out. And then you can use your power rule for the second term here. So I would add 1 to my power. So I would have x to the 6th. And then I would divide by 6. So I would have minus 1/2 because 3 over 6 is 1/2 plus c. Again, really the best thing you can do here for yourself is just review your derivative rules because reviewing your derivative rules will help you with your antiderivatives. And that is it for our video. Thank you guys so much for watching, and I'll see you soon for some practice.